Let's begin this chapter with some examples. We need to find the height of the tower. We need to find the width of the river. We need to find the altitude of B from the ground. In all the examples above, the distances or heights can be found by using some mathematical techniques which come under a branch of mathematics called trigonometry. The word trigonometry is derived from the Greek words tri, meaning three, gon, meaning sides, and metron, meaning measure. In fact, trigonometry is the study of relationships between the sides and angles of a triangle. The earliest known work on trigonometry was recorded in Egypt and Babylon. Early astronomers used trigonometry to find out the distances of the stars and planets from the Earth. Most of the technologically advanced methods used in engineering and physical sciences are based on trigonometric concepts. In this chapter, we shall learn trigonometric ratios of the angle, identities involving these ratios called trigonometric identities. Before we go into detail of trigonometry, let us consider right triangle ABC as shown. Angle CAB is an acute angle. Position of the side BC with respect to angle A. It faces angle A. We call it the opposite side of angle A. AC is the hypotenuse of the right triangle and the side AB is a part of angle A. So we call it the side adjacent to angle A. The trigonometric ratios of the angle A in right triangle ABC are defined as follows. 1. Sine of angle A is equal to side opposite to angle A, hypotenuse is equal to BC upon AC. 2. Cosine of angle A is equal to side adjacent to angle A, hypotenuse is equal to AB plus AC. 3. Tangent of angle A is equal to side opposite to angle A upon side adjacent to angle A equal to BC upon AB. 4. Cosecant of angle A is equal to 1 upon sine of angle A is equal to hypotenuse upon side opposite to angle A equal to AC upon BC. 5. Secant of angle A is equal to 1 upon cosine of angle A is equal to hypotenuse upon side adjacent to angle A equal to AC by AB. 6. Cotangent of angle A is equal to 1 by tangent of angle A is equal to side adjacent to angle A upon side opposite to angle A is equal to AB upon BC. The first use of the idea of sine in the way we use it today. Note, tan A is equal to sine A upon cos A. Cot A is equal to cos A upon sine A. Hence, trigonometric ratios of an acute angle in a right triangle express the relationship between the angle and the length of its sides. Symbol sine A is used as an abbreviation for the sine of the angle A. Sine A is not the product of sine and A. Using the AA similarity criterion, triangle PAM and CAB are similar. Therefore, by the property of similar triangles, the corresponding sides of the triangle are proportional. So, we have AM upon AB is equal to AP upon MP is equal to AC upon BC. From this, MP upon AP is equal to BC upon AC is equal to sine A. Similarly, AM upon AB is equal to AP upon AC is equal to cos A. MP upon BC is equal to AM upon AB is equal to tan A. This shows that the trigonometric ratios of angle A in triangle PAM is similar to angle A in triangle CAB. In the same way, the value of sine A remains the same in triangle QAN. From our observations, it is now clear that the values of the trigonometric ratios of an angle do not vary with the lengths of the sides of the triangle if the angle remains the same.
Of trigonometric ratios indifferent. We know that if the terminal arm of an angle in a standard position having measure theta intersects the standard unit circle in the point P, xy, then sin theta is equal to y and cos theta is equal to x. Hence, the signs of the trigonometric ratio depend upon the signs of x-coordinate and y-coordinate of point. Figuring out the signs of sine and cosine ratios for different quadrants is very simple. That is because sine ratio corresponds to the y-coordinates of the point on the terminal arm of the directed angle in standard position, and the cosine ratio of the x-coordinate of the, if x is positive, cosine is positive. If x is negative, cosine is negative. If y is positive, sine is positive. If y is negative, sine is negative. Since tan theta is equal to sin theta by cos theta, if both sin theta and cos theta are of the same sign, then tan theta is positive, otherwise it is negative. Two-quadrant x negative, y positive, sine positive. One quadrant x positive, y positive, all positive. Three-quadrant x negative, y positive, tangent positive. Four-quadrant x positive, y negative, cosine positive. Quadrant 1, all are positive. Quadrant 2, sine is positive. Quadrant 3, tangent is positive. Quadrant 4, cosine is.
Now let us calculate trigonometric ratios of 0 degrees and 90 degrees. Let's see what happens to the trigonometric ratios of angle A if it is made smaller and smaller in the right triangle ABC till it becomes 0. As angle A gets smaller and smaller, the length of the side BC decreases. The point C gets closer to point B, and finally, when angle A becomes very close to 0 degrees, AC becomes almost the same as AB. When angle A is very close to 0 degrees, BC gets very close to 0, and so the value of sin A is equal to BC upon AC is very close to 0. Also, when angle A is very close to 0 degrees, AC is nearly the same as AB, and so the value of cos A is equal to AB upon AC is very close to 1. This helps us to see how we can define the values of sin A and cos A when A is equal to 0 degrees. We define sin 0 degrees is equal to 0 and cos 0 degrees is equal to 1. Using these, we have tan 0 degrees is equal to sin 0 degrees upon cos degrees is equal to 0, cot 1 is equal to 1. Sec 0 degrees is equal to 1, cos 0 degrees is equal to 1, and cosec 0 degrees is equal to 1, sin 0 degrees not defined. As angle A gets larger and larger, angle C gets smaller and smaller. Therefore, as in the case above, the length of the side AB goes on decreasing. The point A gets closer to point B. Finally, when angle A is very close to 90 degrees, angle C becomes very close to 0 degrees, and the side AC almost coincides with side BC. Angle A is very close to 90 degrees, side AC is nearly the same as side BC, and so sin A is very close to 1. Also, when angle A is very close to 90 degrees, when angle C is very close to 0 degrees, and the side AB is nearly 0, so cos A is very close to 0. So we define sin 90 degrees equal to 1 and cos 90 degrees equal to 0. Table shown gives the values of all the trigonometric ratios of 0 degrees, 30 degrees, 50 degrees, 60 degrees, and 90 degrees for ready reference. Sin A, 0, 1 by 2, 1 by square root 2, square root 3 upon 2, 1. Cos A, 1, square root 3 upon 2, 1 upon square root 2, 1 upon 2, 0. Tan A, 0, 1 upon square root 3, 1, square root 3, not defined. Cosec A, not defined, 2, square root 2, 2 upon square root 3, 1. Sec A, 1, 2 upon square root 3, square root 2, 2, not defined. Cot A, not defined, square root 3, 1, 1 upon square root 3, 0. Note, from the table above, you can observe that angle A increases from 0 to 90 degrees, sin A increases from 0 to 1, and cos A decreases from 1 to 0. Trigonometric ratios of 30 degrees and 60 degrees. Consider an equilateral triangle ABC. Since each angle in an equilateral triangle is 60 degrees, therefore, angle A is equal to angle B is equal to angle C is equal to 60 degrees. Draw the perpendicular AD from A to the side BC. Now, triangle ABD is either equal to or similar to triangle ACD. Therefore, BD is equal to DC and angle BAD is equal to angle CAD, CPCT. Now observe that triangle ABD is a right triangle, right angled at D with angle BAD equal to 30 degrees and angle ABD is equal to 60 degrees. As you know, for finding the trigonometric ratios, we need to know the lengths of the sides of the triangle. So, let's suppose that AB is equal to 2A, then BD is equal to half BC equal to A, and AD square is equal to AB square minus BD square is equal to 2A square minus A square equal to 3A square. Therefore, AD is equal to A square root 3. Now, we have sin 30 degrees is equal to BD upon AB is equal to A upon 2A is equal to 1 upon 2. Cos 30 degrees is equal to AD upon AB equal to A square root 3 upon 2A equal to square root 3 upon 2. Tan 30 degrees is equal to BD upon AD is equal to A upon A square root 3 equal to 1 upon square root 3. Also, cosec 30 degrees is equal to 1 upon sin 30 equal to 2. Sec 30 degrees is equal to 1 upon cos 30 equal to 2 upon square root 3. Cot 30 degrees is equal to 1 upon tan 30 is equal to square root 3. Similarly, sin 60 degrees is equal to AD upon AB equal to A square root 3 upon 2A equal to square root 3 upon 2. Cosec 60 degrees is equal to 1 upon 2. Tan 60 degrees is equal to square root 3. Cosec 60 degrees is equal to 2 upon square root 3. Sec 60 degrees is equal to 2 and cot 60 degrees is equal to 1 upon square root 3. Trigonometric ratios of 45 degree. We are already familiar with the construction of angles of 30 degrees and 45 degrees, 60 degrees and 90 degrees. Now we will find the values of the trigonometric ratios of these angles, including 0 degrees. Let's begin with the trigonometric ratios of 45 degree. Trigonometric ratios of 45 degree. In triangle ABC, right angled at B, if one angle is 45 degrees, then the other angle is also 45 degrees. That is, angle A is equal to angle C is equal to 45 degrees. Hence, BC is equal to AB. Now suppose BC is equal to AB is equal to A, then by Pythagoras theorem, AC square is equal to AB square plus BC square is equal to A square plus A square is equal to 2A square. Therefore, AC is equal to A square root 2. Using the definitions of the trigonometric ratios, we have sine 45 degrees is equal to side opposite to angle 45 degrees upon hypotenuse. BC upon AC is equal to A upon A square root 2 equal to 1 upon square root 2. Cos 45 is equal to side adjacent to angle 45 degrees upon hypotenuse is equal to BC upon AC is equal to A upon A square root 2 equal to 1 upon square root 2. Tan 45 is equal to side opposite to angle 45 degrees upon side adjacent to angle 45 degrees equal to BC upon AB is equal to A upon A is equal to 1. Also, cosec 45 degrees is equal to 1 upon sine 45 equal to square root 2. Sec 45 degrees is equal to 1 upon cos 45 is equal to square root 2. Cos 45 is equal to 1 upon tan 45 degrees is equal to 1. We know that two angles are said to be complementary if their sum equals 90 degrees. In triangle ABC, right angled at B, let's note down complementary angles. Since angle A plus angle C is equal to 90 degrees, they form such a pair. We have sin A is equal to BC upon AC, cos A is equal to AB upon AC, tan A is equal to BC upon AB, cosec A is equal to AC upon BC, sec A is equal to AC upon AB, cot A is equal to AB upon BC. Now let us write the trigonometric ratios for angle C equal to 90 degrees minus angle A. Sin 90 degrees minus A is equal to AB upon AC. Cos into 90 degrees minus A is equal to BC upon AC. Tan 90 degrees minus A is equal to AB upon AC. Cosec into 90 degrees minus A is equal to AC upon AB. Sec into 90 degrees minus A is equal to AC upon BC. Cot into 90 degrees minus A is equal to BC upon AB. Now comparing the ratios in 1 and 2, observe that sin into 90 degrees minus A is equal to AB upon AC is equal to cos A. Cos into 90 degrees minus A is equal to BC upon AC equal to sin A. Tan into 90 degrees minus A is equal to AB upon BC equal to cot A. Cot into 90 degrees minus A is equal to BC upon AB equal to tan A. Sec 90 degrees minus A is equal to AC upon BC is equal to cosec A. Cot into 90 degrees minus A is equal to AC upon AB is equal to sec A. Findings. Note, tan 0 degrees is equal to 0 is equal to cot 90 degrees. Sec 0 degrees is equal to 1 is equal to cosecant 90 degrees. And secant 90 degrees, cosec 0 degrees, tan 90 degrees, and cot 0 degrees are not defined. Sin into 90 degrees minus A is equal to cos A. Cos into 90 degrees minus A is equal to sin A. Tan into 90 degrees minus A is equal to cot A. Cot into 90 degrees minus A is equal to tan A. Sec into 90 degrees minus A is equal to cosec A. Cosec 90 degrees minus A is equal to sec A. We know that an equation is called an identity when it is true for all values of the variables involved. Similarly, an equation involving trigonometric ratios of an angle is called a trigonometric identity if it is true for all values of the angles involved. We will prove one trigonometric identity and use it further to prove other useful trigonometric identities. In triangle ABC, right angled at B, AB square plus BC square is equal to AC square. Dividing each term of 1 by AC square, we get AB square upon AC square plus BC square upon AC is equal to AC square upon AC square. That is, cos A whole square plus sin A whole square equal to 1. That is, cos square A plus sin square A is equal to 1. This is true for all A such that 0 degrees is less than or equal to A is less than or equal to 90 degrees. So, this is a trigonometric identity. Let us now divide 1 by AB square. We get AB square upon AB square plus BC square upon AB square is equal to AC square upon AB square. 1 plus tan square A is equal to secant square A is true for all A such that 0 degrees is less than or equal to A is less than or equal to 90 degrees. Let us now divide 1 by BC square. We get AB square upon BC square plus BC square upon BC square is equal to AC square upon BC square. Cot square A plus 1 is equal to cosec square A. Note that cosec A and cot A are not defined for A equal to 0 degrees. Therefore, 4 is true for all A such that 0 degrees is less than A is less than or equal to 90 degrees.
Application of trigonometry. Trigonometry helps us to solve practical problems of height and distance. Line of vision. If the observer at the location A is looking at an object B, then the line AB is called line of vision. Angle of elevation. If A and B are 2 points such that B is at higher level than A and AM is the horizontal line through A, then angle MAB is the angle of elevation of B with respect to line AM. Angle of depression. If A and B are 2 points such that A is at higher level than B and AM is the horizontal through A, then angle MAB is the angle of depression of B with respect to line AM. When you look up, it is an angle of elevation. When you look down, it is an angle of depression.